So let's check whether there is really direct proportion here. We can definitely see that as the voltage across the resistor becomes less and less, the current strength through the resistor also gets less and less. If we put it the other way around from the bottom up, as we make the voltage across more, the current strength also becomes greater. The more, but now we need to see, is it by the same factor? So let's check. Let's compare the second reading and the first. So what must you do to the second voltage reading to get the first voltage reading? How do we find that out? We'll simply type in the first voltage, 9.41 divided by the second one, 4.67, and we get 2,01, roughly 2. So we've roughly doubled the potential difference from the second to the first. And if we take a look here, multiply this factor here by 2.14, and what do we get? 4.31. Well, of course there's experimental error, but within error we get to the answer that we started with. In other words, from this reading to that reading, we doubled the voltage, and that was associated with a doubling of the current strength, or if you want it the way we actually did it, from the first reading to the second reading, we halved the voltage, and that was associated with a halving of the current strength through the resistor. Let's do one more. Let's go from the first to the fourth reading. What do you have to divide 9,41 by to get 1,96? How do we find that out? 9.41 divided by 1.96 is equal to 4,8. In other words, 9,41 divided by 4,8 will give you 1,96. So now let's check. Do we have direct proportion? Is it the less by the same factor? So we clear our calculator. 4.32 divide by 4,8, and we get 0,9. So indeed we see that there is direct proportion between voltage and current strength. The more by the same factor, or the less by the same factor if you like. There are two other ways to demonstrate direct proportion. One of them is to plot a graph, and if the two variables are directly proportional, you will get a straight line. So let's use the data that we got and plot our graph. So when the potential difference was 9,41, so each of these lines stands for 0.2. So there we have 9,41, roughly there. And then the current strength was 4,32. So there's 4,23 approximately. There's our point. When the potential difference was 4,67, 4,246, and 7 would be somewhere there. Then the current strength was 2,14. 2,14 is roughly there. When the potential difference was 2,89, then the current strength was 1,35. When the potential difference is 1,96, then the current strength was 0,9. And obviously, when the potential difference is 0, the current strength is 0. When there's no potential difference to push the current through the resistor, then the current cannot flow through the resistor. There's a 0 current strength. We can join these dots up, and indeed, it does make a straight line. This is a characteristic of direct proportion. Whenever you see a straight line graph like this, you know that the two variables on the axes are directly proportional to one another. Current strength is directly proportional to potential difference. Another way we can detect direct proportion is that the two variables, one divided by the other, always gives a constant value. And that fits also with the definition of resistance. Resistance means the ratio of potential difference across a conductor to the current strength through the conductor. In other words, R is equal to V over I. Potential difference over current strength. Potential difference across a conductor divided by the current strength through that conductor. So let's check this for our data. So we are going to calculate potential difference across divided by current strength through. And if we do that in the units, voltage divided by milliamperes, which is what we have here, voltage and milliamperes, then the unit we get is kilo ohms, in other words K. If it had been volts across amperes, our unit would have been ohms. So you could go and convert all of these values into amperes by multiplying by 10 to the power minus 3, and then use that in this calculation, and your answer would be in ohms. We are going to use the values as we have them here, so that our answer is going to be in kilo ohms. 9.41 divided by 4.32 equals 2,18, which is rounded off to 2,2. 4.67 divided by 2.14 is equal to 2,18 again, which we can round off also to 2,2. 2.89 divided by 1.35 is equal to 2,14, which we round off to 2,1. 1.96 divided by 0.90 is equal to 2,177, 2,18 again, which we round off to 2,2. So can you see that this is in kilo ohms, and basically it's always giving 2,2, 2K2. We have an exception over here, and that's to be expected. There's experimental error in this. As you saw, the values were changing on the meters, so that's a cause of experimental error. The meters are also not perfect, so you expect that there's not going to be absolutely perfect data, but it's pretty good. We can see that within experimental error, the resistance of this resistor is constant, and it's a constant value of 2K2, which is anyway what we knew it was. Now, when you do this yourself, you might very well not find 2,2. You might find 2 or 2,3 or 2,1 or something around there because of manufacturing error. When they make these resistors, they usually don't make them perfectly accurate. So we have seen that Ohm's law does apply to this 2K2 resistor, because as the voltage is changed across the 2K2 resistor, the current strength also changes through the 2K2 resistor by the same factor. If you double one, the other doubles. If you triple one, the other triples. If you halve one, the other halves, or whatever it might be. In other words, this 2K2 resistor is an ohmic conductor because it obeys Ohm's law.